In this lecture, we'll be discussing data mining and graph extraction. We're using graph structures to learn something and extract insights about our data. To situate ourselves in the broader course, recall that there are 6 learning objectives for this course. Here we're going to focus primarily on the first 2, talking about collecting and cleaning large-scale data sets, where part of the cleaning aspect is extracting the graph structures. And 2, we'll articulate the math behind techniques for developing these insights for graphs, from understanding who are central in these graphs to evaluating the trustworthiness or authority in graph structures. So the first part here, we're going to focus on network structures, be this websites that link to each other, individuals who link to each other, servers that link to each other, all different kinds of ways that we can evaluate or extract structures of nodes interacting with other nodes. And then for the math part, we'll talk about metrics for identifying important nodes in these graphs. So focusing on graph analysis here. So from this lecture, there are 5 main learning objectives. One is being able to construct graphs from web structures, so being able to actually extract that information from structures on the web. 2 is describing ways where an adversary might try and exploit search engines or how we organize the web. 3 is talking about PageRank and how this algorithm lets us capture some idea of importance in the web graph. Building transition matrices to represent these connections between graphs, and differentiating hubs and authorities as a different way to talk about importance in graphs. So for the first one, on how we construct graphs for web structures. So as you might expect, the web and the internet in general, and the world in fact, is full of graphs and networks of different forms. So you can definitely think about the internet as a network or graph in a number of different ways, from how your computer connects to your router connects to some modem, your modem connects to some ISP, and that ISP then connects to some content delivery network or larger service. Amazon also connects to that ISP, or Netflix connects to that ISP, and that's all a big network of different systems working together to provide services on the internet. Likewise, the web itself is a network of servers that host web pages. These servers are parts of domains, etc. But you can also think about networks in terms of citations. So in this visualization of papers in scientific literature, you can look at authors who cite each other or papers that cite other papers in different domains, where there's humanities that are tightly connected to the social sciences, which are themselves tightly connected to brain research, for neurology or psychology, which are also tightly connected to medical specialties, down to infectious diseases and so on. So you can sort of graph or track the way the web of science connects together. There's also graphs in media networks. So here, this is from about 15 or 16 years ago, where the authors of this paper looked at how political blogs linked to each other, referred to each other, which breaks down pretty clearly in the United States into liberal and conservative or left and right style parties. You can talk about graphs and author networks. So a friend of mine, Alyssa Redmiles, she writes for Scientific American, but she also has written op-eds for Wired. So you can talk about different news sources or magazines and how they're connected through authors who write for multiple sources. And of course, the graphs in social networks or social media that you may be much more familiar with. So Twitter itself has a social network, which has a lot of information about political ideology, for instance. So here on the left, we have people who retweet each other. So all of these dots represent users in Twitter, and lines between them represent whether somebody has retweeted another person. On the right, we have a similar graph, but instead of it being retweets, it's about mentions. And what we find is these different structures tell us a lot about political ideology. The retweet graph on the left very clearly separates into liberal and conservative or Democrat Republican structures, and the mentions graph is pretty different than that, suggesting that conservative or Republican users behave differently on social media this is about 10 years ago. And some of the kind of stuff that I do looks at other kinds of structures in social networks. Like this structure is a very famous one now from Kate Starbird at the University of Washington and some of her colleagues, where they looked at conversation around Black Lives Matter and then overlaid the presence of Russian information, or rather Russian Internet Research Agency, quote, troll accounts, and saw that these accounts run by this agency based out of St. Petersburg actually was pretty prevalent on both sides of the discussion, both the Black Lives Matter on the left and the right, and the All Lives Matter on the right discussion, which told us something pretty important about how these disinformation campaigns operate. But that's not to say that graphs are new. In fact, graphs and the studies of graphs and networks have been around for a long time, popularized by Euler's early work in the Seven Bridges of Königsberg, which is almost 3 centuries old now, trying to identify routes that'll take you across the Sea of Königsberg without crossing the same bridge numerous times, or trying to minimize the number of times you cross the same bridge. And these kinds of problems have been around for a long time. In this particular lecture, we'll talk about a number of different kinds of graphs, specifically directed graphs and undirected graphs, and then we'll add the concept of weighting into that. But there are other kinds of graphs as well, bipartite graphs, multigraphs, etc. So the area of network sciences or graph studies is actually quite broad, and we're only taking a narrow view of it right now. So to talk about graphs, let's base this or ground this in an area that you may be pretty familiar with. So social media, popular application on the web. In Twitter, we can talk about a graph where we have 3 different people or 3 different accounts in Twitter. My account in the bottom right, the account on the left is the European Union Research Commission's account on their Center for Crisis Informatics Research, and the top right is Chato Castillo, is a well-known researcher in crisis informatics. So I can be following this European Research Commission account. This account may follow Chato Castillo, and then Chato may follow this EU account, but none of these accounts follow me. So in Twitter, what we have is what's called a directed graph, that these edges mean I follow this other account, but this other account doesn't necessarily follow me. Whereas in this top, we have these reciprocal edges where Chato follows this ERC account and the ERC follows Chato's account. And we can map this to the web as well. So on the right here, we have an article from the New York Times. And in this article, titled Washington Post Breaking News is Also Breaking, they link to a Washington Post article. So you can say here on the left, this New York Times account, or this New York Times domain, rather, has a directed edge or directed link to the Washington Post. And you could very easily imagine that the Washington Post also cites New York Times relatively frequently, and websites at NJIT may also link out to the New York Times if there's a particularly interesting or impactful article about higher education. But that's not the only kind of structure of graphs. So even going back to the social networking idea, Facebook's idea of a graph is quite different. So in Twitter, we had this idea of a directed graph, where I follow this account could follow somebody else, but just because I follow an account doesn't mean that account follows me. On Facebook, it's different. So say there's a new account, this is Lee, my wife, and there's an account about the University of Tennessee fans, or fans of the University of Tennessee's football program. And my wife and I are ostensibly friends, and my wife is friends with a number of Tennessee Volunteer fans as well. But these edges mean something different. So if my wife and I are friends, this idea of being friends on Facebook is reciprocal. I can only be a friend with somebody if they agree to be my friend. And then once that edge exists, it's bidirectional. It says something about how Facebook views the idea of connections, that 2 people who know each other in the same kind of way, which is different than Twitter. And we call this an undirected graph. So in directed graphs, we have this non-reciprocal idea that I can follow you without your following me. On Facebook, it's different, where you have this reciprocal idea, where 2 accounts are connected, and then they become peers in this relationship. So we can formalize this idea of a network by talking about a network as a collection of nodes and edges, where nodes generally represent some kind of object or entity or thing, and edges represent some kind of relationship between these things. When I talk about graphs or networks, I'll use those 2 terms interchangeably. There's no difference in my language between talking about networks and talking about graphs. A lot of it will be just contextual. As we've mentioned, networks can represent a bunch of different things. So there's the social networking aspect of friends and followers. There's the web mining aspect, or the World Wide Web, where nodes represent websites or web pages, and links or edges represent links between these websites or web pages. Communication servers, like I mentioned, so your computer has a link to your router, etc. And there are many others, from transportation networks to citation networks to biological and protein interaction networks. There's a number of different ways that you can talk about networks in a number of different fields. So from a mathematical standpoint, we can talk about graphs as being this, or a graph G is composed of these two things: V, or vertices, your nodes, and E, representing your edges. And your edges are pairs or tuples of vertices that are connected. So here V1 and V2 would be an edge. So in this case on the right, we see there's a tuple A and B that says there's an edge between A and B, a tuple BC that says there's an undirected edge between B and C, ED, and so on. And generally this set of edges is a subset of the Cartesian product of your vertices. And then the order of these represents whether you're talking about a directed or undirected graph. So here we have an undirected graph where A and B have an edge. If we wanted to make this a directed graph, then this tuple AB would say there is a graph, or an edge rather, from node A to node B. And if we want to represent a reciprocal directed edge from B to A, we would flip the order or add a new tuple with the order B, comma A. When we talk about graphs or networks and what these nodes represent, you should generally be, when you're creating your own graphs, which I have asked you to do for the Module 2 assignment, note that your nodes are generally the same type of thing. So that means that connections between these two nodes also should represent the same kind of relationship. Now, that doesn't always hold, and it certainly is a rule that you can bend or break depending on your context. But in general, at least early on, you should be thinking about, well, all the nodes in our graph represent social media accounts, and all of the links or edges between these accounts represent friend relationships or following relationships or something like that. Now, even with Twitter, we see this isn't quite true, because you can have follower accounts, but you can have follower relationships, but you can also have retweet relationships. So does that mean that you represent those in the same graph, or do you represent following graphs and retweet graphs using two separate structures? That depends on your context. So before we move on, let's give you some more vocabulary about networks. So if there's an edge between A and B, we call A and B neighbors. If F, this node F, has no incident edges, that means that there are no edges connected to it, or no tuples in our set E, then we say F has no neighbors and is what we call a singleton. And we can also allow for edges between a node and itself, and we call these loops, or self loops, which you can definitely have, especially now on Twitter. You can retweet yourself. These kinds of relationships that are maybe not as common, but definitely possible. So we can also talk about the idea of weights or importance, or this kind of way to differentiate edges in our graphs, by talking about weighted graphs. So what we've been talking about so far has been unweighted graphs, where if we have some edge that is a pair of vertices, then in the unweighted case, all edges mean the same thing. But does that really ring true for all cases? Ostensibly, my wife and I are closer in relationship than my wife in the University of Tennessee. So we can capture this by talking about weights, or weighted edges. We add some numeric weight to these edge links. So for example here, my wife and I may have an edge weight of 10, and my wife and the University of Tennessee, she maybe sometimes likes UT more than she likes me, would have a much higher edge weight. And what these edge weights mean, again, is contextual. And in fact, there's a whole area of study about what edge weights mean, and the importance of lowly weight or small weighted edges, and edges that have high weights. So what these edges mean can mean, or what the weights of these edges mean, again, like I said, is contextual. In the context of the web graph, it might be the number of links between two domains. So the New York Times almost certainly links to the Washington Post way more than it links to Fox News or to Breitbart based on ideological positioning. But it could also be duration. So if you talk about social networks, then how long two people have been friends may tell you something about the weight of your edge. Or if you're talking about geographic networks or communication networks, maybe weight means proximity. So we want to send messages across communication links between nodes that are close to each other rather than nodes that are very far away to reduce latency or something like that. So how do we represent and store graphs? So now that we've talked about this idea of having a graph that is composed of vertices and edges, how do we represent this? Because we're going to have to do some processing here. So as I mentioned, we have our edges, which are sets of tuples of vertices. Well, the most straightforward way is to just talk about this in terms of edge lists. So basically, you could think of it as a CSV or an Excel spreadsheet or just a text file. It has a list of all the edges in the graph. And nicely, you can say, well, if we have this edge list, assuming that there is at least one edge for every node in our graph, then this edge list is all you need to characterize the full graph. Though there are some constraints here about, well, what happens with singletons that have no edges, things to pay attention to. So we would just have a list, AB, BC, AC, and so on, in a document that represents all of these edges. Another very common representation for graphs is called the adjacency matrix that lets us talk about graphs in terms of how many nodes there are. So we have a number of nodes in, which is the size of our set of vertices. And our matrix A is this n by n matrix called the adjacency matrix, where the ijth value in this adjacency matrix represents whether there is a connection between the ith node and the jth node. And whether this network is directed or not tells you whether this adjacency matrix is going to be symmetric. So if it's undirected, then if there's a 1 between B and A, there must also be a 1 between A and B. But if it's undirected, we have this triangular matrix. If it's a directed graph, then just because A is connected to B doesn't mean B is connected to C, or B is connected to A rather. So here in this graph or in this adjacency matrix on the right, this is an undirected graph. You can see that from the triangular nature of this adjacency matrix. This matrix actually has a number of different uses, both in terms of characterizing graphs, but also mathematically it has a lot of interesting properties and features, one of which we'll talk about when we talk about the stochastic adjacency matrix and modeling transitions among websites. But there are certainly other options for representing graphs. There are adjacency lists, which is similar to an edge list, but we start off with the node and all the neighbors of that node, which lets us to deal with cases where we have singletons. There's specific markup languages for representing graphs, like GraphML or GML or GEXF, and there are a number of others as well. So there's a library or a number of different libraries for characterizing graphs that you can work with. So NetworkX is a really popular one for Python. There's ones for R. There are ones for, and like I said, numerous other languages. And you could just, if you want to look at all the different kinds of, or a number of different kinds of representations of graphs, you can check out NetworkX's list of reading and writing graphs. So you may rightfully ask, well, what does this have to do with data science? Why do we care here? So in this space, one of the things we want to understand is how do we extract useful insights. One of the ways we talk about insights, or one of the sets of insights we care about, is high quality data. So right now we'll move on to talk about how people may exploit search engines to essentially try and inject low quality data into search results. And we can use the tools or the techniques from data science to understand something about trust or importance in graph structures that help us address and resolve these potential exploits. And we'll motivate this by a particular question of trying to understand how we organize information on the web that makes it available for people to find quickly and easily. Back in the early days of the web, this was done by what are called curated web directories. So you may see or have heard of the Best of the Web, which is an existing directory, a manually constructed directory of web pages that's been around for a long time now, 26, 27 years, something like that. But the issue with these kinds of approaches, where we build these web directories through manual curation, is that they're very slow, time intensive, with the number of new websites that are added to the web daily. This is actually pretty much intractable and really doesn't work well for the international or transnational internet that we now have, where we have to deal with websites in many different languages, these kinds of questions. So the next step was search engines based on techniques of information retrieval. Maybe you've heard of Ask Jeeves from ages ago. Now, this has led to growth in an area of research called information retrieval. The general idea here is if you provide some query, like say you want to find messages about or websites about Amanda Gorman, the youth poet laureate in the United States, you might search for websites that contain her name. Naturally, you might find the Wikipedia page for her, or you may find her website. But if you were only looking for pages that had the words Amanda and Gorman in it, you might also find something like web stores that share t-shirts. Now the reason for this is if we're allowing websites to basically say, oh, I'm relevant to your particular query because I have a bunch of your keywords in my page, then what we do is we leave ourselves open to exploitation, because some adversary can say, well, I don't actually care about how you got to my page, whether you're actually searching for Amanda Gorman. Really, I'm trying to make money. I'm incentivized to get people to my page to buy my t-shirts, regardless of what is on my t-shirt. So this approach really damaged the early versions of search engine technology, because it was very easy for somebody to take a particularly popular keyword, shove that keyword into their web page. Maybe they'll make the keyword invisible or change the color of the text to prevent it from showing up from somebody looking at the page, so they don't the user doesn't immediately suspect they've been duped to get in here, and really pollute the search results for a lot of the early search engines. And there's a lot more sophisticated ways of doing this. So maybe you've seen people putting meta tags into their tops of their web pages that have a lot of keywords, so looking for popular keywords or keywords about the current president or about the Olympics or something, even for websites that have nothing to do with those topics, purely to drive traffic. The book makes kind of a claim about this, that people talk about this or have tried to disguise this kind of behavior using the more innocuous term of search engine optimization, or SEO. It's a pretty popular term and has whole industries and positions at companies devoted to this. But the idea is there's a lot of opportunity here for people to spam these kinds of search engine results through content spam, stuffing keywords that they're hidden or in meta tags, and a number of other ways. There's a whole website on Wikipedia, or a whole page on Wikipedia about all the different ways that you can try and exploit these things. So if we go back to the motivating question about how do we organize the web despite these issues, really this breaks down into two problems. One is finding relevant pages. So this is looking for pages that have the keywords I'm searching for, which can be done using standard kind of information retrieval approaches that just do keyword matching. But also we want to look for pages that are trustworthy, pages that are not owned or driven by adversaries who are trying to get you there on sort of false pretenses. So how do we find pages that do both of these things? The answer to this really is the application of networks, where we make a couple of heuristic assessments here, that pages that are not linked to, pages that don't have very many incoming links from other pages, are likely to be less trustworthy, less interesting, lower quality pages. Whereas pages that have a lot of these links coming into them and are grouped in with a number of other pages are likely more important and likely to be of similar topic. And we'll talk about what that means here or the relevance of the topic aspect in a bit. So if we want to look for pages that are important, we can try and find pages that are embedded in these dense clusters, because things that are well connected, pages that are well connected to the rest of the space are more important. And we can think about this in terms of, from a graphical perspective, if some web surfer is just randomly clicking through links on pages, they're likely to end up in these places, which makes them more interesting from an informational perspective. So how might we do this? Well, a naive solution may be to rank these pages based on the incoming links, the number of incoming links. So pages that have many incoming links are, in some sense, more important. And this actually is a well-known centrality metric in network science called degree centrality, or here in this particular sense, we'll say it's in-degree centrality. So we'll talk about this as a directed graph, and the incoming links are, the number of incoming links a particular node has is its in degree. But the issue is here, if we are having to deal with an adversary, especially in today's world where cloud computing is so easy, an adversary can create a large number of fake servers, and all of them have links that point to the t-shirt shop. They're the t-shirt website that he's trying to get you to go to. So just allowing or just ranking by incoming link still leaves us open to exploitation here. This is what's called link spamming. So how do we deal with this? How do we find important pages that are robust to the keyword manipulation aspects that we talked about, and robust to this link manipulation idea? Well, fortunately, in the late 90s, Larry Page and Sergey Brin created the PageRank algorithm, which really was the foundation for Google and Google's search engine. Yeah, now the idea with PageRank is that if you're given a graph, we want to not just look at the in degree, but we want to have weights for these pages that are based not just on how many people are connected to us, but how many people are connected to the pages that are connected to us. So if we scale this out and say, well, what we really care about are links from pages that are themselves well connected. So the summation for PageRank here is the size of the weight of a given node, how important it is for, or valuable it is for our ranking, is proportional to the sum of all the node sizes for all nodes that point to it. So if we look at this from the standpoint of the adversary can have all of these pages that are linked to his website or t-shirt page that he's trying to get you to go to, but it's likely that these fake nodes aren't going to have any incoming links, that they're not very interesting, they're not very important, so their weights overall should be relatively small if we're trying to say, look for pages that are linked to by other pages that we care about. So if we go back to thinking about the web as a graph, where nodes represent pages, websites in the internet, or websites in the web, and the links from website or web page to web page are directed edges in our network, then what we have is a nice intuition that pages vote on each other, vote on how important other pages are by linking to those other pages. So websites that have just a few links coming into them are maybe less important than websites that have many links going into them. And this makes intuitive sense because you could imagine I create some personal web page for me. Nobody really knows who I am, so no one links to it. But Wikipedia has many pages that link to it. And as a result, we'd make some assessment that Wikipedia as a website is more important than my personal website. So yeah, the idea here is pages with more end links are more important. But to deal with the adversary perspective, then we have an addendum. That it's not just the in degree, the links, the number of links that come in, but really how important are the sources of those links? Are important pages linking to me? And then we can see there's a clear difference. So if my personal page is linked to by Wikipedia and by Amazon, well, that means that my personal page is maybe much more important or much more well embedded in the web than some other random website that has a bunch of links from other no-name websites. Which leaves us with this sort of recursive definition that particular website's PageRank or importance is based on the PageRank or importance of other sites that are in fact linked to it. So we can define this mathematically using a notation where a PageRank for a given node in our graph has some score r sub j for a given page j. And this rank can be distributed across all of its outgoing links. So this is the voting aspect. If I have some particular importance value or rank or score, then when I link to other pages in the web, I get to distribute my importance across all the websites that I link to. So we have this relatively straightforward equation where the particular rank for a given page is the sum of all of the other pages that have linked to it. For each of those other pages, their weight divided by all their out degrees. So all the other links that they connect to distributed evenly across all of their links. Let's sum up just the ones that point to me. And this actually can be calculated relatively easily in distributed fashion using message passing. But I'll give you some intuition for how this works. So say we have a graph like this where at first all nodes have the same weight. You take one step forward and all of these nodes down at the bottom that have now a score of 0, well, they have no incoming links, but they link to a number of other pages. So those pages get slightly more weight based on who's linking to them. And if we take one step more through the recursive or through the iterative definition of PageRank, we get slightly larger nodes based on all these other nodes that are connected to them. So first we see this blue node is in fact linked to by the most other pages. It has an in degree of 1, 2, 3, 4, 5, 6, 7. But interestingly, this orange node also has a really high PageRank because this blue node that has such a large importance factor or PageRank here is only linking to one other node. So all of its vote share goes to this one additional node. Whereas like this blue node in the middle spreads out its authority or importance across a number of other nodes. So you could very easily imagine that this blue node is YouTube, this yellow node is Amazon. Lots of people visit YouTube, many people visit Amazon. These sort of in-between nodes are social media sites, and these bottom nodes are sort of less important random sites that no one really links to. An issue with this sort of evaluation, though, is that it can be slow for really large graphs. And we're very much in that space for the World Wide Web because we're talking about billions of pages. So we need an alternative method for dealing with PageRank or calculating PageRank, which leads us back to our PageRank definition, where we can take this adjacency matrix that we saw before. We'll make a slight modification to focus on an adjacency matrix for this directed graph, where we see the column A tells us what nodes A points to B, and A points to D. The column B is connected to C, the column C shows C is connected to A, and so on. And we'll make one more modification and convert this adjacency matrix A to this stochastic adjacency matrix M, where every edge weight in our matrix is divided by the degree of the source node. We see for node A, it has an out degree of 2, so each one of those two edges has an evenly split edge weight. So each one of those edge weights is 1/2, whereas vertices B, C, and D only have an out degree of 1, so their edge weight is 1. Now, an important thing to note here is that the sum of all these columns should equal 1. As mentioned or as described by construction, this matrix tells us the full distributed weights for all the out degrees for these nodes. So then we can take the PageRank equation that we showed you before, and we can rewrite this using matrix notation. And we see this rank column vector R actually equals this transition matrix, stochastic adjacency matrix M, times this column vector R. Now, if you are sufficiently familiar with your linear algebra, you could see that this vector R actually is an eigenvector of this transition matrix M. So we have this lambda R equals M times R, where lambda here in this particular case is 1, which means that we can evaluate these PageRank scores by looking for the largest eigenvector of M. And we can do this using a trick from linear algebra called power iteration, where we initialize our vector first with 1 over n for every node in our graph. So what this says is we'll start off evenly distributing our page ranks across all nodes in our graph. And then we'll take our transition matrix M, multiply it by this column vector R, and then we will iterate on this. So once we have a new value of R, we'll then multiply M by that, and then keep doing that until we reach some stopping point in our iteration, some point of convergence, or where the delta between our current R and the previous column vector rank is less than some value. And now we have a good estimate for the eigenvector, the largest eigenvector of this transition matrix M. And that, just from that vector, we can read off the page ranks of the nodes in our graph. And this works well for graphs that are strongly connected. What this means is for graphs where you can get to any node from any other node, that there exists at least one path from any page to any other page in the network, then this works well. And what happens is this eigenvector, or the weights in this eigenvector, correspond to the likelihood of some random walk through this graph showing up or landing on one of these pages. That the higher this eigenvector, or the higher this eigenvector's value is for a given node, the more likely you are to just randomly land on that page if you are doing a random walk through the graph. But that's not really how the internet's constructed, right? Or the web is constructed. There are dead ends and neighborhoods in the graph that once you're in, you can't get out of. The book refers to these as dead ends and spider traps. So we have to make extensions to PageRank to deal with these irregular structures, either through transporting or random restarts, these kinds of things. The book has more insight into this. So what I've given you is a general idea of how PageRank works. So now what we want to do is talk about how we integrate that with the information retrieval methods that we talked about before. So if we go back to this query idea where we have a query for Amanda Gorman, this Wikipedia page has the search terms in it, Amanda Gorman, so does her personal page, but also so does this t-shirt sales page. So we can't change that. We can't change that somebody has embedded all these references to Amanda Gorman in their page, but what we can do is integrate this PageRank idea, and then rather than showing here are all the pages that contain these keywords and how many times they contain these keywords, we can now re-rank these pages based on their PageRank. So pages that have large values of R, or large PageRank values, are shown to users first. So we get the largest R, maybe this Wikipedia page. The next largest R is Amanda Gorman's personal page. Maybe there are many pages down between that, and this t-shirt page that is using some strange or illegitimate way to drive traffic has some very small R. This is not a very trustworthy page, so it is far down in the page results. Now that's not to say that PageRank isn't without its problems in solving these issues. So one is that when we talk about PageRank, it's a generic measure for authority or something across the entire graph. It's also only one measure across the graph, and it captures only one kind of behavior, and there are other kinds of importance that we'll talk about next week. And then it's still possible to manipulate these kinds of metrics even though they work across the larger graph. So for this first point about generic popularity or generic metrics, this is clear when we talk about different kinds of topics. So for instance, say you want to look for content or websites or nodes relevant to some particular query, say here Jaguar. But there are different ways that we may interpret this query. Is it Jaguar the car? Is it Jaguar the animal? Is it Jaguar the operating system from macOS from several years ago? If we're only given one large or one metric for ranking across the entire web, how do we zoom in on a particular query? How do we help the user say, what are the sites about Jaguar the animal that should be ranked above sites about the car or the operating system? For the second point about there's only one measure of importance, you can imagine that the kind of value or structure that Wikipedia, or role that Wikipedia holds in the web, where it's this sort of compendium of human knowledge, is fundamentally different from the kinds of information you get from a place like MarketWatch, which tells you, here's what the stock markets are doing right this minute. Odds are Wikipedia doesn't have that kind of information, and it's not supposed to. But both of these sites are important sources of information. Even the kind of information they contain is different. And then I won't go deeply into ways to manipulate PageRank. You can read more about this in the book. It's more difficult, but it's still possible. So how do we address these problems? For the measures of generic, like graph scale or cross graph measures of popularity, one way to do this is with topic-specific mechanisms. So if you are Mozilla, maybe you have a directory that assigns different topics. Or maybe you look at user-specific histories. So I want to say, here are the kind of websites this particular user has looked at in the past. Let's re-rank a combination of PageRank plus the similarity to these vectors. Or we can get into other methods. So one method for this is called the hits algorithm. To get at this idea of there being multiple measures of importance, the hits algorithm says that there's one kind of page or one kind of importance called authority, which is a sort of topic-specific sources or websites that are, or nodes in a graph that are important for a particular kind of thing. And there are other kinds of nodes in the graph that sort of push you to these important, authoritative, single topic sources. So in the Wikipedia case, Wikipedia has many topics of information, and it can send you to many different places in the references, whether it be news information or market information, etc. So you can think about websites like Wikipedia as a hub that sends you to these authority topic-specific sources. And the hits algorithm scores these two different kinds of sites differently. So we'll talk briefly about the way we differentiate these hubs and authorities, but here imagine that you have a set of websites and you query on them by some query queue. That'll give you back a bunch of pages that are relevant to that queue, or in the social media case, maybe it's a bunch of users who have used that hashtag or have tweeted about that particular query. And if you look at the interactions or you look at the graphs or the graph associated with these result sets, these returned nodes, you find that many of them all point back to a common site. So you search for something like Jaguar, the animal, and you see, well, some websites don't point really anywhere. They give you some information, but a lot of sites tend to point to National Geographic, or tend to point to the Discovery Channel, or tend to point to Britannica, or something like that. And this common source that is adjacent to all these result sets tells you something about that common source being important. So imagine you go talk to a bunch of your friends who all share the same interests, and over the course of conversations with 5 of your friends, each friend sort of mentions this other person. Now maybe you should go talk to that person. Or if you're talking about academia, you read 5 papers, 4 of those papers all cite this other paper. That tells you something about this other paper must be somehow important to the structure of this network. So with the hits algorithm, we can say these common sites are authorities, and the sites that point you to these common sites are hubs in this graph. This is a different version than PageRank, and we can talk a little bit about how hits and PageRank are different. First, one of the core differences between PageRank and hits is that hits is meant to be defined by some subgraph, or at least on some subgraph. So you query your graph in some way, you get some subgraph of nodes that are associated with your query, be it websites that have some text on them, accounts that have used some hashtag or follow some particular person, or engage in some topical discussion. So we have this subgraph, and then when we apply the hits algorithm, we construct separate scores for hubs and authorities. So each node, in fact, gets 2 different scores, as opposed to PageRank, where every node gets 1 score. The hits algorithm sort of does this simultaneously and produces both a hub score and an authority score for every node in this subgraph. So This hub score is defined as the sum of the adjacent authority scores. So every hub points to ideally some set of authorities. So that's how we define a hub score. That hub, the number of authorities that exist in the neighbor set or the neighboring set of a given hub tells you how hub-like that node is. And then the authority score is essentially the opposite of that. So for every authority, an authority node should be pointed to by many adjacent hubs. So then we just take the sum of all of our adjacent hub scores or our neighbors' hub scores to give us our authority score. And then we repeat this until convergence in a manner similar to how PageRank may do for the convergence-based definition of PageRank. All right, so that fills out this lecture and the learning objectives today. So we've talked about constructing graphs from web structures and data. We've talked about ways that you might exploit search engines and how we can use insights from graph analysis and data mining to capture something about what are trustworthy or important nodes in this graph. So this lets us address the exploitation problem. We've talked about constructions where we can take a adjacency matrix, turn it into a transition matrix to evaluate PageRank in this space. And then we've talked about different ways to differentiate different kinds of importance, so hubs and authorities here, which will give us a good lead-in to our next part or our next lecture, where we talk about different metrics for importance beyond just PageRank in the hubs and authority scores. As always, if you have any questions, you can post them to the discussion forum.